Even though I said we're moving beyond vocabulary now, there are some basic vocabulary terms that we're going to be looking at and some definitions. The first thing we're going to look at defining is an event. What we're going to call an event is any collection of results or outcomes of a procedure. For example, if we're looking at flipping a coin, that event would have two outcomes. We could either flip a coin and get a head or a tail. If we're rolling a die, we could either get a 1, 2, 3, 4, 5, or 6 if it's a standard die. Those are things that we would call an event. A simple event is an outcome or an event that cannot be further broken down into simpler components. That's a simple event. A sample space for a procedure consists of all possible simple events. That is, the sample space consists of all outcomes that cannot be broken down any further. In finding probabilities, which is what we're going to be doing here, we're going to need to determine how many elements are in our event and how many elements are in our sample space. Let's look at an example problem. It says, in the following display, we use B to denote a baby boy and G to denote a baby girl. The procedure that we're looking at in this first example is the single birth of a child. The event, if we're interested in producing a girl, would be one girl, if we're looking at the probability of having a girl. Our sample space, if we have just one child, would be the birth of either a boy or a girl. The way we come up with our event, our probability here, is the probability of an event will be equal to the number of elements in that event divided by the number of elements in the sample space. If we're interested in producing a girl, then the number of ways we can come up with a girl in the birth of one child is 1 out of 2 outcomes, boy or girl. So that's why we say there's a 50-50 chance of having a particular sex. If we're looking at the birth of 3 children, suppose I have 3 kids and I want to know, my event would be to have 2 boys and 1 girl. I could do this by having 2 boys first and then a girl, a boy, girl, boy, a girl, boy, boy, and these would all be simple events in the event of having 1 girl out of 3 children. So in this case, the probability out of 3 births would be equal to, there's 3 different ways that I could come up with 1 girl out of 3 children, and then here we have our sample space. These are all the possible combinations for births of boys and girls if you're looking at 3 kids. And there's a total of 8 elements in our sample space. So the probability of having 1 girl out of 3 births would actually be 3/8. The notation we're going to use, the P that I used right here, is for function notation. It means the probability. It's a probability function. E here would be our specific event. Typically we use A, B, C, D, E for our events. You can use any variable you want. Remember, the uppercase letter is what we're going to use for our event. So P of A would denote the probability of an event A occurring. And I just kind of took you through an example up here with these problems. There's 3 basic rules for computing probabilities. The first one would be the empirical rule. This is where you take the number of elements in your trial and divide it by the number of elements in your sample space. Okay, you're actually doing an experiment or doing a trial. So if I sat here and I tossed a coin 10 times and I counted the number of heads that came up, and if I got 3 heads out of 10 coin tosses, I would say the empirical probability for getting a head out of tossing a coin would be 3 out of 10, or 0.3. The theoretical probability, though, would be what we just did in the previous example. The theoretical probability, first of all, assumes an equally likely outcome. And that would be the number of elements in your event divided by the number of elements in your sample space. I should change this word sample. It's not really sample, it's the number of trials, because we're actually performing a trial. We're actually doing something. On 2, we're looking at a theoretical probability, where we take the number of theoretical elements in our event divided by the number of elements in the sample space. And then the third type of probability or rule for computing probability is a subjective probability. This is what weathermen use. The subjective probability is really just an educated guess. Now, weathermen make their predictions. For example, the chance of rain on Thursday was like 60%, and most of us got rain last Thursday. the weathermen used models and based on past behaviors and cold fronts coming in and moisture coming up from the Gulf, and they knew that when they converged on this one area, it was going to get some rain, and there was a pretty good chance. So they assigned a 60 or 80% chance of rain. But it's an educated guess based on models. Number 4 here is actually a problem out of your book, and it is a subjective probability. And I want you guys to take a minute and do this. It asks us to estimate the probability that the next time you ride in a car, you will not be delayed because of some car crash blocking the road. You will not be delayed by a car crash. Do you think that probability would be high or low? It's going to be high because most of the times I get in my car, drive around, I don't see any accidents on most days, especially on a clear sunny day. So we could assign a probability, let's say 0.998. I don't know. It could be 0.999 for all I know. It's a subjective probability. It's an educated guess. It's not a guarantee that I won't have a wreck or see a wreck. So I've got to put something in there a little under 1. A probability of 1 means it's guaranteed to happen. So I am not guaranteed that I get in my car and drive home without any events, any traffic accidents. But the chances of it happening are very, very small. So I say the probability that I get in my car and not have an accident or see an accident is very high. All right, number 6, it says U.S. presidents. Who was the 4th president of the United States? This would be a 14th president of the United States. This could be a question on a history test. It's multiple choice. They tell you, hey, Taylor, Fillmore, Pierce, or Buchanan. If you make a random guess for the answer to that question, what is the probability that your answer is the correct answer of Pierce? 25%. And how did you come up with the 25%? There's one correct answer out of 4 choices. One correct out of 4 choices. And we're assuming that you're just as equally likely to guess any one of the 4. So we have that equally likely assumption here, and this type of probability then would be considered a theoretical probability, whereas on number 4 it was a subjective probability. All right, the law of large numbers. It says as a procedure is repeated again and again, the relative frequency probability of an event tends to approach the actual probability. The relative frequency probability is the empirical probability. The actual probability is our theoretical probability. We're going to go through this experiment. I want everybody to, if you need a coin, I got coins, just give them back. We're going to actually toss coins. I want, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 14, 15 counting me. If everybody tosses a coin 10 times and keeps track of the number of heads, we're going to get a whole bunch, 150 coin tosses. All right, so I got 6. How many did you get? All right, let's add these up. So we got 81 out of 150 heads. Somebody do the math on that for me. 54%, 0.54. All right, very good. The theoretical probability is 0.5 for tossing a coin. Some of us would have gotten 0.3. Some of us would have gotten 0.8 when we were tossing the coin if we just did 10 coin tosses. But as the sample size increases, the empirical probability is going to become more like the theoretical probability. That's what the law of large numbers gets us. That's why we like to take large samples of things whenever we're doing statistics. You don't want to base your survey results on only 3 people. You want to survey a large group of people and see if, to kind of get an idea of what's going on. So that's a quick application of the law of large numbers. All right, so here's an example problem. It says when 3 children are born, the sample space is as follows. Now, it's easier to come up with the sample space, I think, if you align this vertically. Start with boy, 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 so there's no girls, and then we introduce one girl, and then we just move her through the birth order. You see how that works? And then we have 2 girls, 1 boy, so we're going to have 2 girls, 1 boy, and move the boy through the birth order. And then finally we have 3 girls, and that's how you come up with the sample space for the birth order of children. It says, assuming that boys and girls are equally likely, find the probability of getting 3 children of all the same gender. This is our event, 3 children of all the same gender. So that's going to be our event. How many elements are in our event? Well, our event consists of boy, 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 or girl, girl, girl. 3 kids all the same gender. So that would be the probability of our event then is the number of elements in our event divided by the number of elements in the sample space. So there's 2 elements in our event. How many elements in the sample space? 8. And that reduces to 1/4 or 0.25. So the probability of having 3 of the same sex children would be 0.25. What type of probability is this? Empirical, theoretical, or subjective? Theoretical, because we're assuming that we have an equally likely chance of having a boy and a girl. A simulation is what we do whenever we want to not actually physically do what we did. For example, tossing the coins. I could have used a table of random digits like what we have here, and I could have come up with a simulation where instead of tossing all the coins, I can assign values like even digits are heads and odd digits are tails. So I could have said, okay, well, even digits, and those would be 0, 2, 4, 6, 8. Those would be simulate a head, and odd digits, 1, 3, 5, 7, 9, would represent having a tail. So instead of tossing those coins 150 times, we could have looked at these numbers, and they're grouped in blocks of 10, in blocks of 5. So here's 5 digits that would represent, this would be a tail, head, tail, tail. Do you see how I can use these random digits then to simulate tossing a coin? Because if I asked you to go home and toss a coin 500 times and come back with the results so we could compile it, your thumb would be getting sore by the end of the assignment, wouldn't it? We could use a random number table in order to simulate tossing the coin. This author, I think, as he's the one that I read that in the past, he had given that assignment where he asked students to go home and toss a coin 500 times and bring the results back to class. And he took up the papers and he glanced through them, and he could tell right away who actually did the assignment and who just made up numbers thinking, oh, I'm not going to do this, my thumb is sore, I'm just going to make stuff up. And how he could tell is when you're tossing a coin, it's not unusual to have a streak of, say, 7 or 8 heads or tails in a row. But when people are making up coin tosses, rarely would they put a streak of 7 or 8 heads in a row. When we did this coin toss with our 10 people, I would not have guessed 8, but somebody got 8 in their coin tosses. I would not have guessed 2. Same thing. It just seems like it's an unusually low number. Mine actually came out fairly even. It didn't exactly alternate, but it just happened that way. But when people make up these things, they don't put those extreme values in there. But in 100 coin tosses, it wouldn't be unusual to see a streak of 7 or 8 of something in a row. Anyway, that's how we can use simulations instead of actually doing the experiment. It's cheaper to run simulations. It's easier to use simulations for things. Now, the probability function is actually a function. That's why we use function notation. Just like in algebra, we say y is equal to f of x. Y is a function of x. Well, here, the probability is a function of an event. The range here of the probability function goes from 0 to 1. It is impossible to have a probability less than 0. 0 means that something is impossible. You cannot have a probability greater than 1 because 1 represents 100%. It means something is guaranteed to happen. So the probability has values, numerical values between 1 and 0. It's easy for us to change these numbers into percents just by multiplying by 100. So if I say there's a 45% chance of something happening, that 45% corresponds to a probability of 0.45. The probability of an event that is certain is 1, impossible is 0, and we can take on any value in between. There's something that's left out here, and that is the probability of a sample space has got to be equal to 1. If we consider every possible outcome and we take the probability of the sample space, that has to be equal to 1. Because how did we find probabilities again? We took the number of elements in our event and we divided by the number of elements in the sample space. So if this truly is our sample space, we're going to have the same value on top as we have on bottom here, which means the probability of the sample space is 1. Here's a question. When rolling a single die, what is the probability that the outcome is 7? Do y'all know what a die is? Yeah, the probability is 0 because there's 6 sides on a die, right? And you can't get a 7. 6 is the highest number. So the probability of that outcome is going to be 0. It's impossible. Complementary events. The complement of an event A is going to be denoted by A bar, and that consists of all outcomes in which the event A does not occur. So if we have a rectangle here that represents our sample space, and inside of it we have an event A just using area, then this would be a complement outside of here. The probability or the total area here would be equal to 1 if we let area represent probability, because the probability of a sample space is 1. So the total area here would be 1. And then I could use the area of this circle to represent the probability of A, and the area of... I used a prime here for the notation. Other books use a prime for the complement. Your book chooses to put a bar over things, which gets confusing, I think. Also, the probability of an event plus the probability of the complement of an event has got to be equal to 1, because you either have the event or the complement. That's it. If we let the event A be the probability of rain, then what would be the probability of no rain? 1 minus the probability of rain. If I told you the probability of rain is 20%, what would be the probability of no rain? 80%. So the probability of an event is equal to 1 minus the probability of the complement. It's another way of looking at it. Here's an example problem. It says 1,010 United States adults were surveyed and 202 of them were smokers. So it follows that the probability of randomly selecting a smoker would be 202 out of 1,010, or 0.2. So then I ask you, well, what's the probability of randomly selecting someone that's not a smoker? It would be 0.8. 1 minus 202 divided by. All right, rounding off probabilities. When expressing the value of a probability, either give the exact fraction, and when it's a nice fraction like 3/4, give the exact fraction. It's okay. Or 1/6, or give the rounded off decimal to 3 significant digits. So, for example, when a probability is not a simple fraction, such as 2/3 or 5/9, express it as a decimal so that the number can be better understood. All digits are significant except for the zeros that are included for proper placement of the decimal point. So in number 18, it says, when rolling a pair of dice at the Bellagio Casino in Las Vegas, there is a 1 in 36 chance that the outcome is a 12. If we were to round that 1 in 36 into a decimal, we'd go to our calculators, 1 divided by 36. And to round this to 3 significant digits, we would type in 0.02 what? 78. The 0 is there as a placeholder. So we would write 0.0278. 3 significant digits. That means 3 numbers that are not 0. An event is said to be unlikely if its probability is very small, such as 0.05 or less. 0.05 is kind of the standard cutoff for us. An event has an unusually low number of outcomes of a particular type, or an unusually high number of those outcomes if that number is far from what we typically expect. On some of these problems, common sense is going to reign. Assume that 700 births are randomly selected and exactly 171 of the births are girls. Use subjective judgment to determine whether the given outcome is unlikely, and also determine whether it is unusual in the sense that the result is far from what is typically expected. And we say the answer is C, because it's unlikely, because there are so many other possible outcomes that have similar or higher probabilities. It would be more likely to get a number that is closer to 350, not 171. It's not that it's unlikely because it's not exactly 350 births. There's just a whole lot of higher probabilities, numbers with higher probabilities. It's very difficult to get exactly 350. That probability is not as high as you think it would be. The probability of 350 or less would be 50%. But the theoretical probability is 0.5 here. The second part of this question says, determine whether exactly 171 girls out of 700 randomly selected births is unusual. And yes, it is unusual, but not because girls are more common than boys. Actually, there's slightly more than 50% chance of having a boy. Did y'all know that? I think it's 0.55% of the births are boys. But baby girls are stronger at birth, so they're more likely to survive. So the species needs more male births in order to have about 50% of the males survive and 50% of the females. It is unusual because it is not about 350 as expected. About here is the key word. This answer here is actually going to be B. We expect about 350, not exactly 350. Okay, we expected a number closer to 350 than 171. And once again, this is subjective probability. It's not computing a theoretical probability. Subjective is difficult because it's more touchy-feely and it's not as precise. A theoretical probability is hard and fast, 50% chance. So a 50% chance of having a girl out of 700 births, we would expect 350 girls. In your book, you'll be reading a problem about a genetic research company that hopes to be able to improve the odds of having a girl, a couple having a girl. And you'll read about the results, and then you can determine if you think that procedure is effective or not based on their results.